Hello everyone. Today let's solve the problem number 572, subtree of another tree. So you can just go through the problem. You can just try to understand the problem with the help of the example they have clearly mentioned here. So I'll just summarize the question so that it will be easier to understand. So what the question states here? So we are given the roots of two binary trees. So we are given the roots of two binary tree, not single root. We have been given the roots of two binary trees. One is root and another one is subroot. So then what is our main task here? Our task is to determine whether subroot is a subtree of root. So here you can clearly see subroot, whether this subroot, just give me a second here, whether this subroot is a whether this subroot is a subtree of root or not. So what is a subtree here then? Subtree starts at the same node in the root. Here you can clearly see subtree starts at the same node in the root. It includes the node and all of its descendants. It includes the nodes and all of its descendants, right? And the structure and the node values must match exactly. Structure here, that's what they have given here. Structure is same and also the node values must match exactly. Here you can clearly see 4, 4, 1, 1, 2 and 2. Here the node values also match exactly, right? In this case, we have to give the output, we have to return the output as true in this case, right? Else we have to return false. That's what they have given here. You can clearly see here. Let's consider example 2 here. Root they have given 3. Here this one subroot starts from here 4. But here according to the subtree definition, what a subtree states here, subtree means subtree starts from the same node in the root. 4, 4, it starts from the same node in the root. It includes the nodes and all of its descendants. Yeah, it includes the nodes and all of its descendants as well here. 4, 1, 2, 1, 2 here in this case. But the structure and the node values must match exactly. And here they have given it includes the node and all of its descendants. In this case, descendants, we have an extra edge here. So this one, extra edge from 2 to 0. Here, this is not containing the extra edge here. So this will be considered as this whole thing. But here, it doesn't consist of the extra edge to 0, from 2 to 0. So this is considered to be false. So the output that we need to return here is false in this case. So you can clearly see here. I hope the question is completely clear. Let's discuss the approach first, followed by the edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, let's discuss the approach. So I'll just explain the approach here itself. Just give me a second here. So yeah, we'll be making use of the recursion, right? We'll be making use of the recursion to solve the problem in two parts here. So just remember, we'll be making use of the recursion to solve this problem in two parts. So what is the first step here? Let's segregate this one into two steps. Let's discuss the first step first. So we have to check if the subroot is same as root. So we'll be making use of the helper function is same. In this case, we'll be making use of the helper function is same. You can give any name. In my case, I have considered is same. So let's make use of this function. So we will be making use of the helper function is same. What does the helper function is same do here? It checks if the two trees are identical or not. It checks whether two trees are identical or not. That is the reason we'll be making use of the helper function is same here. So if they are identical, then we will return the output true in this case. I hope this is clear. So this is the first step that we are dealing with. So next, let's discuss the second step here. So while I say second step, we are traversing the we have to traverse root to find the subroot, right? So if root itself matches the subroot, then we have to return true. If root itself matches the subroot, then we will be returning true in that case, right? Only if we have 412, here also 412, root and subroot matches here. So that's what I am saying here, right? Suppose forget this one. So if root itself, suppose if this is the root here, and if root itself matches the subroot directly, then we have to return true in that case. Otherwise, we will recursively check the left and subtrees. In this case, let's consider this one now. Otherwise, we will recursively check for left and right subtrees, right? So that's what we'll do. This is the approach that we will be going with. I hope the approach is completely clear. Let's discuss the edge cases one by one and then finally write the. So let's discuss the edge cases one by one. First thing is basic match case. So I'll just give here basic match case. When I say basic match case, I'm just speaking of this one. Root is directly equivalent to the subroot. So root, let me consider here 1, 2. Here then subroot, let me consider here 1, 2 here. So the output will be true in this case. Why the output will be true here? This root matches the subroot, right? Here we have 1, 2. This one is root actually, and this one will be subroot. Same thing, 1, 2, right? So this is for the condition basic match case. So let's move on with the second edge case. Nothing but this one, single node match. So when I say this one is for the single node or single node match. So I'll just give here single node match. So input, let me consider here single node. I'll just give here 1. You can just take any number. So I'll just give here subroot. Let me consider here 1. Same thing. Here output will be true here in this case, right? So here because root we have only one element here, and subroot here also we have only one element. So this matches this one, right? So the output is true here. This is for the condition single node match. Let's move on with the third edge case. Nothing but single node mismatch. So when I say single node mismatch, so let me give here single node mismatch. So let me consider here root 1 here, subroot, let me consider here other element. So here this will be 2. The value of the node differs here, right? So the output will be false here. So root, this will be 1, and subroot, this will be 2 here. The value of the nodes differs, so the output will be false here. This is for the third edge case. Let's move on with the fourth edge case here. Subtree not found. So here we don't have the subtree at all. So subtree not found. So here for this one, let me give here subtree not found. So let's consider here input root equals let me give here 1, 2, 3 in this case. Subroot, let me consider here 2, 4. In this case, it will be like this. Root will be 1, 2, and 3. So subroot will be here 2 and 4, right? So here subroot doesn't exist at all here, right? So the output will be false here. Subtree not found. Even though subroots exist in the root, too. Here, this one you can clearly see here. Subroot exists in the root. It does not match this one completely. We should have 4 here, right? If we had 4, then it would have been true, right? Let me just 1 second. This is fine. So the output will be false here. These are the 4 edge cases that we need to remember. First edge case was for the basic match case, and the second one was for single node match. Third one is for single node mismatch, and fourth one or the final one was for the subtree not found. So I hope all the edge cases are clear. Next, let's start writing the code now. So here, as we had discussed in the approach, so if root is null, then subroot cannot be a subtree, right? So we have to return false in this case. So I'll just give here if not of root, then we will return false. This is fine. Then let's go with one thing. Let's go with the next one. Let's check if root and subroot are the same tree, right? We'll be making use of the recursive function in this case. So let's write the recursive function this one for this one. Then let's make use of the function here, of that function that we have written here. For the recursive function, I'll just go with here is same. So we have discussed this one during the approach itself, right? We'll be going with the recursive function, helper function or the recursive function. So I'll just give here, we'll be making use of the recursive function or the helper function, right? I said that one during the approach. So here, if both nodes are null, then they are said to be identical. We have discussed this one. So if not of P or not of Q, then P equals Q. This is fine. Next step is if node values are different, then they are not identical, right? If they have the same structure, still the value differs, then they are not said to be identical. How can we write this one? If value of the P not equal to value of the Q, then we'll just return false, because values doesn't match. Finally, we have to recursively check if left and right subtrees are identical or not. So I'll just give here return. Let's make use of the function here, recursive function is same. Sorry, what did I give here? Is same of e dot left, comma q dot left here. So I'll just copy the same thing and make the necessary changes to the right subtree as well. Here instead of left, let me give here right. Here instead of left, again let me give here right. I hope this is clear. So we are just making use of the helper function. Now in the main function, so here we can just check if the root and subroot are the same tree or not. Let's make use of the recursive function here. So let's make use of this function here is same of root and subroot, right? So we have the parameters root and subroot here. Let me copy this one. Let me paste it over here. Root and we are just checking if root and subroot are the same tree. If they are, then we are returning true, or then we have to return true here if they are same. Finally, we have to recursively check in the for the left and right subtrees, or in the left and right subtrees as well. So let me go. Let me return here. Let me make use of the recursive function is subtree. In this case, is subtree of left. We have to recursively check in left and right subtrees, right? So initially, let's check for the left subtree, and this one root will be left subtree, right? So this one has to be root dot left, yeah. And subroot will remain same, subroot itself. Or I'll just copy the same thing. We have to recursively check for because we have to recursively check in left and right subtrees, right? So left we have already done. For the right, this one I'll just make as root dot right. Subroot remains same. I hope this is clear. So let me format the code once and let me hit the run button. Hope that works. Runtime error. Is same is not a function. It is saying is same is not a function. So yeah, what mistake I have done here is so the bracket here. So I have closed this one here, right? This one, let me remove this one, this bracket, and let me place this bracket here over here. So this is fine. Let me format this one once and let me hit the run button. Still saying p dot while not applying cannot read properties of null. So what mistake I have done here is it says here cannot read properties of null. This one is not related to this one here. If both the nodes are null, then they are said to be identical. That's what we are doing in this line. So I have to return this one, right? Return whether we are comparing p equals q, the values. So I have to give here a return. So I forgot this one. Let me run this code again here. So yeah, now you can clearly see the sample test cases are getting passed here. So let me hit the submit button. So you can clearly see here all the test cases are getting passed. So the code works. This code works absolutely correct. So I had missed this one here. So return I had missed. This is fine. So let's quickly discuss the time complexity and the space complexity here. The approach that we went with here is recursion. We know that one, right? We are making use of the recursion here. So what would be the time complexity here? The time complexity would be big O of n into m here. So n into m, or you can consider m into n as when here. So sorry, n into m, let me consider here. So n is nothing but the number of nodes in the root here. In this case, n is nothing but the number of nodes and m is nothing but the number of nodes in subroot. This one, number of nodes in the root, m is nothing but the number of nodes in the subroot. In the worst case, we are comparing, in the worst case, we have to compare subroot at every node in the root, right? So the overall time complexity would be here big O of n into m, or you can consider big O of m into n. So what will be the overall space complexity here? The overall space complexity would be here big O of n. Why the overall space complexity here would be big O of n? Because in the worst case, we are comparing the skewed tree, right? Recursive calls can go up to the n depth. So overall space complexity here is big O of n. So we now know that overall time complexity is big O of n into m, and this one overall space complexity here is big O of n. I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.